Hello friends, I am Amir Nizami and today we are going to solve cross-ply plate problem using the three-dimensional abacus. Okay. So we will solve three-dimensional solution with abacus. So let's start. So first of all, before going to the abacus directly, we have some background of that. Okay, so in abacus modeling, what we do, we have the options there for the two-dimensional or three-dimensional modeling space. So depending upon the choice, okay, we may choose the solid elements or shell, wire or a point. Okay, so we have to focus mainly on the solid and the shell in both two-dimensional and three-dimensional contexts. Okay, so if we have a solid and a shell in abacus, so solid is what? A three-dimensional or a two-dimensional representation of a physical object with volume. Okay, so basically it's a confusion here at a two-dimensional, but even though it's a 3D only, and everything is 3D, but we represent a plane stress or a plane strain problem like a two-dimensional. Okay, so we give the depth or some other dimensions itself in the abacus only. So the presentation of the cross section is given so that it's mentioned as a two-dimensional, even though it's a solid. Okay. So in 3D, solid part has a length, width, and a depth. Okay. And in a two-dimensional, a solid part is represented as a planar area with a thickness. Okay. So solid elements are used to model the structures where the stress and strain distribution through the thickness is important. Now the shell is used to model the thin structures. If we are taking away thin plates, okay, A by H ratio is 50 or 100, then it's fine. Okay, it's good. Or if we are modeling for the moderate thick plate, A by H equals to 20, like that, then also it would be fine. Okay. But for a more depth, like A by H equals to 4, which is a very deep plate. So for that, we have to go for the solid. That's a better option. Okay. Now, we may see when we open Abaqus, so we have like this. One option is the choosing from the modeling space a 2D planar, or other dimension we have the three-dimensional option. Okay. So both side we are having options of that. Okay. So if we choose this on the 3D, if we see on the 3D modeling here, okay. So we have the deformable. Okay. Here we have the option of the solid choosing, okay, and then exclusion. But if we see in the two dimension, this one, so what is in the 2D? So we have the 2D planar, okay, deformable, but here there is no option of the solid. Okay, here it is shell. Okay, so in Abaqus, solid itself taken into account by a different name like plane stress and plane strain conditions. Okay, so that's the different thing. So it's absolutely correct to point out that the 2D modeling in Abaqus, there is no explicit solid. Okay, so we see here in the 2D, they have not mentioned in the 2D planar, they have not mentioned here solid. Okay, they have shell, wire, and a point. Okay, but in the 3D here in the Abaqus, it is mentioned as solid, shell, wire. Okay, here we can see. So that's the difference between 2D and 3D. But even though we have just before discussed that 2D also there is 2D solids, okay, and 3D solids. So that's the thing we have to understand. So Abaqus take 2D planar, okay, and they do not include the solid in it because they mention in a separate way, like plane stress or not plane strain condition like that. Okay. So let's have the further clarity here. So we can see here, okay. So we are seeing the 2D. So in 2D, if we see, okay, so there is the option of plane stress condition and a plane strain condition. Okay, so whatsoever we are choosing, so that's the from here. Okay, so 2D solids it is itself, but they don't include the solid by explicitly. They are not using that term. Okay, so that's the thing here. So 2D modeling, they are including here plane stress or a plane strain condition. Okay, so often referred to as 2D solids in practice. Okay, when we study the finite element, we use 2D solids, but here in Abaqus, that is not using by itself. Okay, so here they are explicitly using the name axis symmetry shell wire. Okay. So while the term solid is not explicitly listed in the 2D, okay, base feature, the plane stress strain axis symmetry options are effectively used to model the 2D solid problems. Okay, so this was the main confusion students are having. So that's the main thing what I want to clear. Okay, now Basically we are interested here in modeling the 3D. Okay, so we want the exact solutions to model. Okay, basically we know that it's a finite element method. Abaqus is based on FEM approach, so it is an approximate method, but as much we find the mesh, it would be more close to the exact results. Okay, so we want to model a cross-ply plate. Okay, so we will try to model it. So using the 3D stress element. Okay, so we want to model it purely three-dimensional stress element. Okay, using this. So this is the standard element type, okay, for 3D solid models, and it is used generally for 3D stress analysis, okay, where the stress strain are fully three-dimensional. Okay, so it is fully three-dimensional element. Okay, and the element families are, if we take the linear element, then it is 8-noded linear brick C3D8, and if we want to take 20-node quadratic brick element, then it is name is C3D20. Okay, and the other option is going for the continuum shell also, and the continuum solid shell also. Okay, but what we are interested right now in modeling the exact 3D. Okay, so not exactly, basically it's definitely an approximate 3D, but hence fully three-dimensional. It's correct to use this fully three-dimensional, okay, to analyze the stress strain. So we will go for this. Okay, so here it is the same thing is just explained here. Okay, so the standard element type is 3D solid models, where we can see we are choosing the element as family of element as 3D stress. Okay, so we will do full 3D analysis, and the element we have seen C3D20 for a quadratic element. Okay, so another was the continuum shell element. Okay, it's also a family of 3D elements on 3D solids, but we have here continuum shell elements, and another option we will see there is continuum solid shell also. Okay, so we will see these things later. Okay, first we are interested mainly in the 3D stress, so it is the continuum solid shell element. Okay, now why no explicit solid option in 2D is given. So we have just discussed these things, okay, because they have in the Abaqus it's mentioned explicitly plane stress, plane strain, and axis symmetry. That's why it's not mentioned solid there. Okay, and we can see when the 3D general 3D solids elements are used. Okay, so 3D stress elements are used for this modeling the exact fully 3D solutions. Okay, full 3D stress strain, while in the continuum shell it's good for the thin structures and very thin structures for the continuum solid shell. Okay, so these are the basics we have to see. Now we are interested here, we will work on 3D stress. We will choose the 3D stress elements and model full 3D stress analysis. Okay, so basically what we are going to do, we are going to model a plate, okay, where the plate dimensions length and width. Length along the x direction would be 120 mm, length along the y direction would also be 120 mm, and thickness here would be I think let's take 120. A by h should be 4. Okay, a means length along the beam, so a by h total height we want that should be 4. So h should be equals to, if a is 120, so what should be 120 by 4? That would be 30 mm. Okay, so total thickness should be 30 mm. Okay, so if we take the 3-layer element, then each if would be equal h1, h2, h3. Okay, so let's see. So we are keeping here the length along x, length along y, and length that is 120 mm, and each thickness is 10 mm. Okay, each lamina here it is shown as 0, 90, 0. Okay, so 0 degree, 90 degree, and 0 degree again. So we are having this, and then the material properties are given here. Okay, these are the material properties given. E1, E2, E3, nu12, nu123, nu13, and G12, G13, and G23. Okay, so now we will start modeling. We will go to Abaqus. Okay, so first of all, we will go to file, set the directory. Okay, so let's set directory. It's in temp. Let's give the name here itself 3D or cross-ply 3D. Okay, 3D, let's say. So okay, we may do one thing here. We'll make one folder here, new directory, and 3D Cross-ply. Okay, okay. So now we are having this. We are not related here. So Cross-ply 3D. We have Cross-ply temp Cross-ply. Okay. So we have there. Okay, in temp we are having this Cross-ply 3D. Okay. Now we want to save the file. Okay, so we can save here. So save as. We want Cross-ply 3 layer. Okay. Okay. Now, so we will start. So we know from where we start. We will start with the part. Okay. So we will go to part, and we are modeling the 3D solid. So we will use 3D. Okay. And then it's deformable, and it's a solid. Okay. Exclusion. Continue. Now it's showing this. Now we can see here X and Y and Z is inside this. Okay, while our modeling, if you see the plate here, okay, just if you see here, so Z direction is in the upward direction, so we will model like this only. So if we see from that Abaqus XY, okay, so how we will model XY here, length along X is 120 and length along Y is 120. Okay, so we have to model here LX and LY in that way. So let's choose, okay, rectangle 0, 0, okay, and then let's do 120, 120. Okay, so XY is already made here. Okay, so this is X and Y. So that's fine. Then we will do done. Now it's asking the depth. So what is the depth? Means what is the thickness of the plate? Along the Z direction we are having 30 mm. Okay, so we may keep here as 30. So keep the 30. So now we will, okay, so we have got the plate here. Now if we rotate it in such a way, now we can see we got like that. Okay, now the Z direction is along the thickness direction, and X and Y along the length along X and Y direction. Okay, fine. Now what we do, we have to part. Okay, we have to just make it the datum we have to choose. So we'll go to tools, we'll go datum, okay, and then we'll go to the plane, okay, where we have to make the datum, and let's say offset from the plane. So we will make offset, so inter value. So we want in the downward direction. Okay, so flip. So now it's along that direction, and now we will say, okay, how much? We know that total thickness is 10 mm, and if we want 3 layer of equal thickness, so 10, 10, 10. So first offset should be made at 10 mm. Okay, so we are making it first offset 10 mm. Okay, so it's made now, and then again we will select this plane, and then another datum inter value in the same direction here, and at what, 20 mm. Okay, so it's already 20. Fine. So we can see here we got two datum plane. Okay, so one two at 10 mm and another at 20 mm. Okay, now we will partition it. So what to do? Now we will go tools, partition, and we will select from cells. Okay, and then use datum plane. So what we made the datum, we will use this, and we will create partition. So the first partition is made here. Okay, then it is asking for the select the cells to partition. We will select these cells, and then done, and then it is asking for a datum plane. So the another datum plane is this one which we want to partition. It's created. So both we can see now, both the data and plane, it's created the partition already. It's a 3 layer now. Okay, so what we want here, we made it. Now we will go to assembly. Okay, so we went to assembly and the create. Okay, so we want independent mesh. Okay, fine. So this is made. Now we will go to property and we will put the property here. So material, basically we are making a cross-ply 3-layer plate, so only one material would be used, and elastic. Okay, now here if we see, so not isotropy, we are going to give engineering constants. Okay, so E1, E2, E3, so we will have to put here E1, E2. So what's the value of E1? Let's see from here. E1 is 25,000. Okay, so we'll give here 25000. Okay, E2 is 1000, E3 is also 1000. New 12 is, I think, 1 by 4, that is 0.25, again 0.25, and new 23 is also 0.25. Okay, then we have to see G12. So let's see G12. G12 is 500. So we'll give G12 as 500. G13. So what's the value of G13? 500. And then G23. So let's see the value of G23. G23 is 200. Okay, so we'll give here 200. So the material properties are fed here. That's fine. Then let's assign it. So create section. So we will create the section homogeneous. Fine. Continue. So material 1 only we have fed, so that only material would be there. Okay. Fine. So we have assigned the section. Dismiss. Then create. Select the regions to be assigned a section. Okay. So we will use one by one. So this is the top one. So we are assigning it. Then okay. Okay. Then we will select second set. It would be also done. And then we will see third one. Set 3. Done. Okay. So it's already done now. So we have assigned all the 3. Okay, section 1. So in all material 1 set 1, set 2, set 3. So each individually we have assigned here. Okay. So now we will assign. Okay. Go to assign and we will assign the material orientation. Okay. So let's assign the material orientation. So select the regions to be assigned a local material orientation. So select it. So if you assign the first top layer, so how to assign here? Okay. So basically, if we select the regions and say done, we will go here, use default orientation, and now what we want, we will go for the coordinate system. Okay, so from here we have chosen the coordinate system, and then we are going to the axis 3. Okay, along the z direction we are choosing. What's the angle we are providing? We are going to formulate cross ply, so 0 degree. Okay, so we are giving a 0 degree, and then we will choose here. So this is the cross coordinate. Okay, now the regions to be assigned local partition is for this second one. Then again we will do the same, and we will choose here coordinate system. Okay, along the axis 3, and the angle is what here now? 90 degrees. So 0, 90. So we have made it 90 degree. Fine. And the third one we will choose. Okay, use default. What we are going to see? Coordinate system 3. The angle should be 0 degree here. Okay. Okay. So we have chosen 0, 90, 0. Okay. So it's done. The material voltage is also done here. Okay. Now, if we have completed this material orientation, then what we have to do? We will go to step and let's see. We will create step static general. Okay, continue, and it's by default what it is, it's fine, just okay. Okay, then you may see from here they have a field output. So what the field output is there, you can see from here stresses they have chosen, same strains are also there. So we can say total strains, we don't need plastic strain and all. So first of all we will just take total strain. Okay, and then displacements, let's see. So translation and notation is fine, and then the force the reactions are there, that's fine. Okay, so we may specify the points. Okay, so for each layer, if we choose the point, let's say 1 2 3 4 5 6 7 8 9. Okay, so at each interface if we take 9 points, let's say, choose it. Okay, now this means we have the also H output, HQ output, we didn't require it. Now we may go further, load here. Okay, now what is here, creating a load type. So we may choose here the load, concentrated force, moment, okay, surface traction, pressure. Okay, any type of load we can choose from here. So let's say we have chosen here pressure, continue. So what it is asking for, it is asking for the surface. Okay, so let's say we are interested on the top surface, top line. So we have to choose the surface here now. So we will choose this surface. Okay, and we will say it done. So it's asking uniform. So we may have the uniform pressure also, we may apply the sinusoidal pressure also. Okay, so we are using right now uniform pressure, and magnitude as let's say 1 magnitude we are applying. Okay, we will say okay. So it's uniformly distributed load is acting on it. Okay, we have applied the UDL load, and only at the top we have applied this. Now let's say boundary conditions. So we will create the boundary condition. So simply supported boundary condition on each side. Okay. So boundary condition 1, let's say displacement boundary condition apply. Okay, on this edge we'll apply. Okay, so then what we want, along the x there would be the possibility of displacement, but it would not displace along the y direction and the z direction. So y direction means u2 direction and z direction is u3 direction. It should not move. Okay, hence it's a 3D solid element, so there is no relation of the rotation. Okay, no need of that. It's fine. Then we will have. Okay, now if we are modeling the model on this side, if we are going the same thing we will give. Okay, and the boundary condition would be same. Okay, let's create another, we have to make it create boundary condition 2, displacement, continue, and this is the set 2 that we have chosen, done. And along this also, it's along the x direction is allowed, so u1 is allowed, u2 and u3 is not allowed. Okay, so we will say okay. Now what, now we will model along this y equals to 0 and b. So again we will say create displacement, continue. So this would be the third set. Okay, so we will say done. And now along this is along the y direction, so along y the displacement is allowed, not along the x and z. Okay, and then this is our part. Okay, so again we'll create, continue, done. Again what is the u1 allowed and u3 allowed, u0 not allowed, sorry, and you only in the u2 direction allowed. Okay, dismiss. Now what more? We have made this. Now we have to mesh. Okay. So we may go to the mesh. We may have element type. Okay, so select the regions. Select the regions. Then okay, so what we are using 3D stress. Okay, family. Okay, standard. We are using 3D stress. So it's completely fully 3D stress analysis will be there. Okay, we want to choose quadratic element. Okay, if we take linear, then it is C3D8R. Okay, and if we take quadratic, then it is C3D20R. Okay, R is the reduced integration. Okay, so we are choosing this. Fine, and select the regions to be assigned the element types. So done. Okay, so it's already we have done, no issue. And if you see the element our verify mesh, no, so we are choosing this element type. Done. Okay, then what we have to do, we have to mesh it. So let's say we are taking it's 10 mm, what we should take, let's say 2 or 3 mm, let's say 5 mm. Okay, okay, yes. So we can see here, to get better results generally we have to fine it more fine, but computational cost will increase. So just to show the results, I'll try it. And here's the job. Let's say create job 1, continue, and let's run it. So data check. Check completed. Now we'll submit it. Submitted. It will take some time. Once we have taken a very coarse mesh, so it would be soon we will get the results. But that's not the exact results. You have to mesh it finer. Okay, that's why the convergence study are done to get the more accurate results. So 5 mm is a very coarse mesh here. Okay, I think we get completed successfully. So you can see the results now. We'll go to this one. Yeah, so now you can see results from here. Okay, so at this edge we can see the results. 090 for a cross-ply laminated beam using the uniformly distributed load. The results what we are getting here like this. Okay, so we may see various other deformations in plane displacements in magnitude u1, u2 and all. Okay, so from here we can see how u1, u2 and all are given here. u2, okay, and u3 means the, so at the edges on all the sides, and how it's at the center it is given. We may also see the plot here. If we try, let me try it, x0 and y v by 2, okay. So choose at this position to see the warping, okay, along the x direction displacements. So what I should do, I should tools and path, create, continue. So I'm choosing here, okay, done. Okay, now I will go to this xy and I will go to this path where we have created. Come and let us try to plot u1 first at that position. Okay, plot. So we can see the warping, okay, in plane displacement or the zigzag displacements here, okay, what we get from the Pagano's paper, but there we have seen that that is given for the sinusoidal distributed load, okay, and also the mesh, to get those results accurate we have to mesh it very fine, but here we have done for the uniformly distributed load, okay. So we have to change the loading type and then we can compare with the Pagano's load. So but here we to show that, okay, we are getting the warping, okay, how is we are getting the warping of the in plane displacement. Okay, for the this is ux, okay, along the x direction. Similarly, if you want to find v, so we have to choose a different point for those results. Okay. And also we can see here, if we try shear stress, let's see whether we are getting S13 what. So okay, but hence it's a very close mesh, so we are not getting very good results. To get a good results we have to find it. And another is 2 3, is there any possibility? No, that would be 0 here at that position, something like that. Okay, S11, no, S11 at the mid we have to check, x by 2 and y by 2. Okay, S12, no, those are not the results here. Let's see u2, whether u2 is there or not. No, u2 would be 0 at this position. Okay, so basically we have to choose the different locations. Okay, so we have chosen 0b by 2 to get u1 only, and we are getting the results for that. For u2 we have to choose a by 2, means on this position we have to choose here. Okay, so let me show you. If you want to choose for that, basically this is z, and this is y, this is, okay, this is the exact way. Yeah, now it is z xy. So if we want to choose for the v direction to plot, then we have to choose here on this position. X is a by 2 and y is 0 here. Okay, so we have to choose this location to plot the v results. Okay, in plane displacements v. Okay, and similarly for the w, if you want to get the maximum, so we have to choose the center point so that we can get the maximum transverse displacements there. And because at the edges we know there would be no displacement, so transverse displacement would be 0 at the edges, but at the middle we will get the maximum results. Okay. So we are closing here, and inshallah next time I will try with the different loading case and all. Okay, so thank you.